This video is the second half of a review covering many concepts that we've learned so far in the first semester of AP Calculus. For the first half of the review, go ahead and click the link that will appear in the upper right-hand corner. Number 19, consider the function given by h of x equals 9 times arcsecant x minus the square root of x squared minus 1, restricted to the domain of x being greater than 1. Find an expression for h prime on this domain. Then choose the answer that is equivalent. So the bottom line is I need to take this whole function and find h prime. So I'm going to start by rewriting this ever so slightly, focusing on this part right here. So I have h of x equals, I'm going to leave this part alone, 9 arcsecant x. But when it comes to this part, I'm going to write it with a fractional exponent. So this would be the same as the 1/2 power. So if I want to take the derivative, so I want to do h prime, I'm going to just take the derivative one term at a time. And in fact, when you take the derivative and you see a constant in the front, that constant can just sit there as you take the derivative of whatever comes next. It's time for me to remind you of a fact that you should have memorized. The derivative of arcsecant x is 1 over the absolute value of x times the square root of x squared minus 1. So that's what we see here, so I'm just going to go ahead and plug that in. On my next move, I'm going to do two things. Notice that none of the answer choices have absolute value in there anywhere. And that's because we're told that the domain is x values greater than 1. So x is guaranteed to be positive, so I don't need the absolute value. So I'm going to take those away. Also, when multiplying by 9, we're just going to wind up multiplying by 9 in the numerator. So I'm just going to put the 9 in the top. So there's the derivative of the first term. Moving on to the second term, I'm going to do the power rule and the chain rule. So I'm going to have the 1/2 in the front, and then reducing this power by 1 gives me negative 1/2. And then I've got the inner function of x squared minus 1. And because of this inner function, I have to do the chain rule and multiply by the derivative of the inner function, which would be 2x. As we begin to simplify this, notice that we have this 1/2 in the front, and then we have this 2. So those will cancel each other out on the next step. Also, we have a negative exponent, so that's going to drop this down to the denominator. So that would be 1/2 power in the denominator. But then we also know that the 1/2 power is the same as the square root. So I'm going to transform this into a square root in the denominator. So I'm going to have the square root of x squared minus 1 in the denominator. The x is still there, so I have this. So in order to combine these into a single fraction, like we see among the answer choices, I need like denominators. So they are almost the same, except for the first denominator has this x. So if I were to multiply by x over x, then I would have like denominators. So that will give me x squared. So I really can go ahead and look up here and see what the answer is going to be, because I'm going to have 9 minus x squared over this common denominator. So right away I see the 9 minus x squared in choice C and D. So which one has x radical x squared minus 1? Well, that's option C. So option C is the answer. Number 20 refers back to function h from problem number 19, for which we found the derivative, which is shown here. On the domain x is greater than 1, the graph of h has exactly one horizontal tangent line. Find the x-coordinate at which it occurs. Then state whether h has a relative minimum, a relative maximum, or neither at that x-coordinate. Justify your answer. Relative extrema occur at critical numbers, and that's where h prime is equal to 0, or where h prime is undefined. This fraction will only equal 0 when the numerator is equal to 0. So we have 9 minus x squared is equal to 0. Adding x squared to both sides, we have 9 equals x squared. Taking the square root of both sides, we have x is equal to plus or minus 3. So we have two critical numbers so far. So these are possible locations of relative extrema. Small correction, we are dealing with a restricted domain of x greater than 1. So that leaves out the negative 3. So we have one critical number. X is equal to 3. Now let's talk about where h prime is undefined. This fraction will be undefined where the denominator is equal to 0. I have two factors in the denominator. So normally I would set each of them equal to 0, and I would say, well, x equals 0, and then I would say the square root of x squared minus 1 is equal to 0. But again, we have this restricted domain, x is greater than 1. So that means we will forget about x is equal to 0. That's not an option. So we're left with this part. If you square both sides, right away the radical goes away. So really we just have x squared minus 1 must equal 0. Adding 1 to both sides, we have x squared is equal to 1. And taking the square root of both sides, we have x is equal to plus or minus 1. However, restricted domain strikes again. X is greater than 1, not equal to 1. So both of these are out. So this is the only possible location of the relative max or relative min. To determine whether there is a relative max or a relative min, or neither, at x equals 3, we need to put this number on a number line and make a sign chart. So here's negative 3 on this little number line. I am going to have 3 rows on my sign chart because I'm looking at the following 3 factors. I have this one factor in the numerator, so that's going to be 9 minus x squared. But then in the denominator, I have 2 factors. I have the square root of x squared minus 1. And then I have this extra little factor of x, which gets its own row all to itself. So we need to determine if these factors are positive or negative in each one of these intervals. I should put a 1 right here, okay, with a parenthesis, because remember x has to be greater than 1, so we're not going past 1. Wait, that was silly. I put negative 3. This is x equals positive 3, of course, because like I just said, x has to be greater than 1, so negative 3 wouldn't have even made sense. So let's examine these factors and decide if they are positive or negative in each interval. So in the first interval, we need a test value that is between 1 and 3. So I guess how about 2? Let's picture a test value of 2. So this first factor would be 9 minus 2 squared. That would be 9 minus 4. That would be a positive number. Okay, if I put a 2 right here on this factor, that would be 2 squared would be 4, minus 1 would be 3. It's a positive value. And of course, if x itself was 2, that's a positive value. So overall, we got nothing but positive going on here, so this is going to be positive. And really, if I think about it, there's no way for a square root to give you a negative number. So I don't really have to think about it very hard. Okay, this is also going to be positive in this interval. So we're talking about numbers that are bigger than 3, like 4. And so if, for example, if x is 4, that's obviously positive again. But what about this one? If x were 4, then this would be 16. I'd have 9 minus 16. This would be a negative number. This single negative means that overall, I'm going to have a negative value from these 3 factors. So h prime would be negative in this interval. We have learned that when the derivative is positive, the original function is increasing. And when the derivative is negative, the original function is decreasing. This helps us visualize that we must have a relative max at x equals 3. Let's write up our summary and justification. But when you write your justification, do not mention the original function h. We are going to justify using the first derivative test, so make sure you are only using the first derivative in your justification. H of x has a relative max at x equals 3 because h prime changes from positive to negative. A point P moves along the curve given by x squared plus y cubed equals 9, whose graph is provided here. Point P moves so that dx dt is equal to 3. Problem number 21. When P is at the point 1, 2, what is the value of dy dt? So I think we need to do some implicit differentiation. Let's take the derivative of both sides, d dt. Squeeze this in here so that we can make dy dt show up. So I'm going to take the derivative of each term, but remember we are differentiating with respect to t. So none of these variables are t. So we're going to have to do the chain rule for each term. So taking the derivative of the outer function here, I will have 2x. But then I have to multiply by the derivative of the inner function, which is just dx dt. Moving on to the second term, same deal. The derivative of the outer function is 3y squared, but then I multiply by the derivative of the inner function, which is dy dt. The derivative of a constant is 0. So we are supposed to find dy dt. We are also given this extra fact that dx dt is equal to 3. So let's go ahead and substitute 3 in right here. Kabam! And then we have 2x times 3, which will be 6x. Let's subtract 6x from both sides. So this is going to move over here and become negative 6x. Now let's divide both sides by 3y squared. So 3y squared will end up in the denominator right here. So this is a valid answer, or you can do that tiny amount of simplification and come up with this. Wait a minute, this is not the final answer. We need to evaluate when p is at 1, 2. Let's practice using proper notation for evaluating a derivative at a point. So we would write dy dt, and to show that we are evaluating at a point, we put a vertical line and write the point at the bottom of the line. This means we will substitute 1 for x and 2 for y. I'll use the simplified version that we have. So that would be negative 2 times 1 divided by 2 squared. This equals negative 2 over 4, which of course simplifies to negative 1/2. Number 22. Water is draining out of a conical tank at a rate of 3 cubic meters per minute. The tank is 12 meters across at the top and 12 meters deep, as shown here. The volume of a right circular cone is given by this formula, where r is the radius of the base and h is the height of the cone. Show that the volume is equal to 1/12 pi h cubed. Interesting. There's an easy relationship between the radius and the height for this particular cone. So notice that the diameter of the opening and the height of the cone are the same. But what about the radius? So for the whole container, the height is 12. The radius would be 6. So you can see that the radius is half of the height. But I need you to understand that that will be true at any height. So say if the height was right here. Still, the height and the diameter are going to be the same. So this would be the height and the height. But then the radius would be half of that diameter. So the radius is always going to be half of the height. So this is the relationship that we can use to simplify the original volume formula. So if the volume is equal to 1/3 pi r squared h, but r is 1/2 h, then we have that the volume is 1/3 pi 1/2 h squared h. I just substituted 1/2 h in for r. If we square 1/2, we get 1/4. So this becomes volume equals 1/3 pi 1/4 and then h squared times h. But you can see that we have h squared times h right here. This is going to be h to the third power. And then 3 times 4 is 12. So we get volume is equal to 1/12 h to the third power. And then we've got that pi, which I'm just going to stick that in the numerator. Actually, I want it to match what they have there. So I'm going to go ahead and write it the way they have it. So this would be 1/12 pi h cubed. So we showed it. Problem 23. At what rate is the depth of the water, h, changing at the moment when the water's depth is 4 meters? Include units. I always like to start off by making an inventory of facts that we know. In the setup, we are told that water is draining out at a rate of 3 cubic meters per minute. This is the rate of change of volume, and it will be negative because the water is draining out. So we know that the rate of change of volume is negative 3 cubic meters per minute. We also know that we are dealing with the moment in time when the depth of the water is 4 meters, and that's h. So at this moment, h is equal to 4 meters. So these are the facts that we know. Now let's add on what we are looking for. At what rate is the depth of the water, h, changing? So we are looking for the rate of change of h. In other words, we need to find dh dt. Looking at the variables in our inventory, I see that we need a relationship connecting volume and height. Let's use the simplified formula for volume that we found in problem number 22. Volume is equal to 1/12 pi h cubed. Let's go ahead and take the derivative of both sides with respect to t so that we can make dv dt and dh dt appear. When you're finding the derivative and there is a constant in the front, you can just leave the constant alone and go ahead and find the derivative of whatever comes next. So really, this is what we're doing. On the left side, we have dv dt, and then we have the constant, which I'm just going to write as pi over 12. The derivative of h to the third power is 3h squared. Because the variables do not match, we have to do the chain rule and multiply by the derivative of the inner function, which is dh dt. Let's look back at our inventory for things that we can substitute. For example, dv dt is negative 3. So I can put negative 3 right here. H is 4, so I can put 4 right here. We need to solve for dh dt, but I think it will be easier if we go ahead and simplify this down a little bit. So 3 goes into 12 4 times. So now I have negative 3 is equal to pi over 4 times 16, because I have 4 squared is 16, dh dt. But now 4 goes into 16 4 times. So that gives me negative 3 is equal to 4 pi times dh dt. All I have to do is divide both sides by 4 pi, and that should be the answer. So dh dt is equal to negative 3 over 4 pi meters per minute. I'm getting the units because we have the change in height divided by the change in time. So that's meters over minutes.